Hello everyone, welcome to my YouTube channel TechSpot. This is me, Harish Gopale. So basically in today's video, we are going to discuss about the working and functionality of SR flip-flop by using NOR gate and the RTL design implementation of SR flip-flop. You can see the block diagram of SR flip-flop on my screen. Basically it is one of the synchronous sequential circuit design which is used to store one bit of information. And if I talk about its functionality, so it's always samples data on positive edge of clock. Okay, you can see it has total three inputs. One is set, reset, and clock, and two outputs, that is Q and Q bar. Below you can see the logical diagram of SR flip flop, where we have used two additional AND gate, which is connected to the SR latch by using NOR gate, and this is how it becomes SR flip flop. Okay, as we have two main inputs, that is set and reset, so we can have four combinations. So let's discuss each combination to understand the whole functionality of SR flip flop by using NOR gate. So the first combination is 0 and 1, where my S is equal to 0, R is equal to 1. Beside you can see the truth table of NOR gate, which helps us to understand the whole functionality and the whole behavior of this SR flip flop. Basically it tells if my one of the input is high, then we can predict the output is 0. Okay, so now let's understand. For this AND gate, the input is 0 and 1, so output is 0. For this AND gate, input is 1, R is equal to 1, clock is equal to 1, so output is 1. Okay. For this NOR gate, my input is 0, so like we can't predict the output directly. But for this NOR gate, my input is 1, so I can directly predict the output 0, because what truth table says that if one of the input is 1, we can say output is 0. So now Q bar is 0. This Q bar is going as a feedback for this NOR gate. Means 0 and 0. As per the truth table of NOR gate, it is 1. So we got Q is equal to 1. Here we got complement of Q bar, that is Q is equal to 1. That means when the value of S is equal to 0 and R is equal to 1, my flip flop is in the set state. Now the next combination is inverse, that is S is equal to 1 and R is equal to 0. So for this AND gate, clock is equal to 1, S is equal to 1, output is equal to 1. For this, clock is equal to 1, R is equal to 0, so output is equal to 0. Now again, for this NOR gate, my input is 1, so I can directly predict Q is equal to 0. Okay, now this 0, now this Q is going feedback for this NOR gate, so 0 and 0, Q bar I got 1. So means if my S is equal to 1 and R is equal to 0, so my SR flip flop is in the reset state. Okay. Now the third combination is 1 1. S is equal to 1, R is equal to 1. So clock is equal to high. So for both the AND gates, my output is high only. Okay. Now for both the NOR gate, my input is 1. So I can directly predict output is 0. So Q is also is equal to 0. Means I can't see here the complement. Means this is invalid state. So means if S is equal to 1 and R is equal to 1, that means my SR flip flop is in the invalid state. Okay. Now the last combination is 0 0. So again, my clock is high, so for this AND gate my output is 0. For this AND gate is also my output is 0. Now for both the NOR gates my inputs are 0 0, and we can't predict the output Q and Q bar. So here the Boolean expressions for this Q and Q bar will help us to get the output and to understand the behavior of this flip flop when the S and R both are 0 0. So let's understand the Boolean expression for this Q. So for Q, Boolean expression will be 0 nor with Q bar. Okay, 0 nor with Q bar. Okay, so as per the De Morgan's theorem, this whole bar will break and it will become 0 bar and Q bar and bar. 0 bar will become 1 and the whole bar will cancel and it will become 1 and Q. So at the end output will be Q. Means whatever we will provide Q, we will get the same. Means it will hold the previous value. Okay. Now same for Q bar. For Q bar my Boolean expression will be 0 nor with Q. Okay. So again, as per the De Morgan's theorem, this bar will break and 0 bar and Q bar, again 0 bar is equal to 1 and Q bar is equal to Q bar. So whatever we will provide, whatever the value Q will be there, we will get as it is. Means my flip flop is in the hold state. Okay. Now let's jump for the design implementation of this SR flip flop by using NOR gate on a board. So here you can see on my screen, I have already written an system Verilog code for the design implementation of SR flip-flop. So let's discuss each line of code. Here you can see the model name is SR flip-flop. I have taken four inputs, that is clock, set, reset, and one is reset in. Okay, and two outputs, that is Q and Q bar. Okay, and for in system log we have separate for always have a procedural block for the design implementation of sequential circuits. So I have used always have at the rate passage of clock, as I told you. Like it works on every, it samples the flip-flop samples data on every positive edge of clock. Okay, and then we have condition if not of reset, then if it is not in the reset, okay, then as I have taken the reset in, so that time output will be 0. Okay, inside and else I have case statement. We know the functionality of case statement. If you are using case statement, then we have to provide output for every we have provide input for every possible outputs. Okay, okay, so as we have two signals, set and reset, so we can have four combinations, as we have explained in uh, explain while functionality. Okay, so as per the truth table of SR flip-flop by using NOR gate, if it is 0 0, then my flip-flop is in the hold state. So what I have did, I have assigned Q to the output Q and Q bar to the output Q bar. If the yes is 0 and R is 1, then as per the functionality, it is in a set state. Means 1 I have assigned logic 1 I have assigned to the output Q and 0 to the output Q bar. If my S is 1 and R is 0, then it is in reset state. So according to that, I have assigned 0 to the output Q and 1 logic 1 to the output Q bar. And when it comes to 1 1, so my SR flip flop is in the invalid state. So you can see I have assigned X to the output Q and Q bar, because it is a behavioral logic. What we are implementing, behavioral logic. Okay. Now when I have execute this code, then I got this schematic where you can see the our input yes are clock and reset n. Okay, and we can see, you can see the two flops, two registers, one for Q bar and one for Q, and these are the muxes because we have used some case statements, that's why we got these muxes. Okay, how to verify this SR flip-flop, I have written a simple test bench code also. Let's discuss that code also. So here you can see the test bench code where I have taken module, test bench, SR flip-flop. Same inputs which I have taken for the design implementation, that is also I have taken for the test bench implementation. Set, reset, clock, reset n, and two output, that is Q and Q bar. This is the instantiation. And here I am toggling clock at 5 nanoseconds. Okay, 5 nanoseconds because my time scale I have defined, that is 1 nanosecond divided by 1 picosecond. And inside the initial begin, I have initiate some values for the yes and R and resets. Initially my reset is 0, so if it is reset 0, then as per the behavioral logic, my output will be 0. If it comes out of the reset, then it will work as per the functionality of the sub flip flop. Okay, so when we run this simulation, we will get the waveform. Let's understand. So here you can see the waveform, here you can see my S is 0 at this 0 to 10 nanosecond, R is 1, and my clock is also toggling. But if you see, my reset n is 0. So as per the behavioral logic, I have assigned if it is in reset, then my Q and Q bar is 0. So till 20 nanosecond my reset is 0, so output is 0 0. After 20 nanosecond my reset goes high. Now here my clock is also toggling. Now here if you see, my S is 0 and R is 1. So at this time my flip-flop should be in a set state. So here you can see the output Q is high and Q bar is low, that means it is in a set state. On next passage of clock, my S is 0, S is high and R is 0. So my flip-flop should be in a reset state. So here you can see Q is 0 and Q bar is equal to 1. So my flip-flop is in the reset state. As per the behavioral logic, we are getting the outputs. When S and R both are 0, so as per the functionality, my flip-flop should be in the hold state. So here you can see that flip-flop has hold the previous value. The previous value of Q was 0. So here also Q is 0. Previous value of q is q bar, so here you also get q bar. Now when yes and r both are high, then the flip flop should be in the invalid. The flip flop should be in the invalid state. So here you can see I'm getting invalid value. Okay. So basically in this video we have successfully discussed the working and functionality of SR flip flop by using NAND gate, as well as we have discussed the RTL design implementation of SR flip flop by using NOR gate. Sorry, NOR gate. Okay, and test bench code also we have discussed, and we have discussed the waveform also. So here I will stop the video. If you are watching this video, then please click on like button, and if you are new to this YouTube channel, then please subscribe to my YouTube channel. Thank you so much.